Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're continuing on our quest to understand the nature of Big Bang cosmology. We've gone through the nature of what homogeneity and isotropy are, which balance the concepts of what we can expect across the cosmos. Then we went and looked at the redshift of the universe and how it's expanding with time. We've even seen how the cosmic microwave background informs us about the nature of what the universe was like when it was 300,000 years old. And Big Bang nucleosynthesis shows us where the helium all came from in the early cosmos when the universe was only 3 minutes old. However, since all that time, the universe gets older from the beginning, and gravity works on everything that's inside the cosmos. It pulls things together and makes them clump and form groups, and therefore changes how galaxies appear as they look through time. And so that's what we're going to talk about, is the formation of structure, large-scale structure in the cosmos as a result of Big Bang cosmology, the last pillar of Big Bang cosmology. Well, first, we see that this particular cluster, the Virgo Cluster, is one of the closer clusters of galaxies. It's rather massive. It's about 67 million light years away and composed of a few thousand galaxies with a couple of supermassive giant ellipticals in it and numbers of other galaxies. It's the largest group of galaxies in our neighborhood, and we used to be called the Virgo Supercluster of galaxies upon which this was centered. Other clusters of galaxies are prominent, such as Abell 2305, and this is a Northern Hemisphere galaxy cluster. We can see there's lots of elliptical galaxies and a couple of supermassive giant ellipticals in them, and we see that matter is condensed together to form these structures of clusters and groups. And here's a no more distant galaxy cluster, much more distant, Abell 2352, and we see that there's lots of little galaxies way in the distance that look very, very, very faint and very tiny, but you can definitely see them clustered together. Now, if we then look more locally, we see what's called the Laniakea Supercluster, and the Laniakea Supercluster encompasses many, many, many of the local clusters of galaxies around us, centered roughly on the local group. There's also the Virgo Cluster, as well as other clusters of galaxies that make up this supercluster of galaxies, where there's roughly about 100,000 of these things stretched out almost over approximately 500 million light years. And there's approximately 10 to the 15th solar masses. There are 4 subparts. Each of them were considered separate subclusters, but the Laniakea supercluster has been shown to be gravitationally bound. And so this is a large, large cluster that is bound gravitationally. So how do we know that things like this, that are this large, are bound gravitationally, especially with masses of 10 to the 15th solar masses? Anyway, that's an open question. So our next question is, we can then say, well, looking at the centers of these galaxy clusters, say the Virgo cluster or any of these others, like the ones we just saw before, and if we look in X-ray light, we see that there's a huge amount of hot gas dominating the starlight. In fact, there's much more of hot gas surrounding these inside the dense clusters than there are actually stars or starlight. So we only see about 1% of the mass of the galaxy when we're looking in visible light, because vast majority of it is this hot intra-cluster gas. If we look at some of these groups, we see that some of them can be on like the cluster 7047. These various clusters show that there are giant ellipticals in the center of them, surrounded by this hot gas. And there's lots of little globular clusters as well, at globulars, which would be barely visible in this. But all the spherical objects aren't globular clusters, but separate galaxies that are clustered together. And so where does this hot gas come from? How does that appear? And here's another view of it. This is a view of galaxy cluster Abell S740, and it's about 450 million light years away. These things are incredibly distant. They're on the order of hundreds of millions or tens of millions of light years away. Not tens, hundreds of millions of light years away. And the center of it is dominated by a massive giant elliptical galaxy that has maybe 100 billion stars in it. But what we see more importantly is this diffuse halo, which the diffuse halo is actually the X-ray bound cluster, is the diffuse halo of X-ray emitting light, it surrounds it. It also tries to map the dark matter as well. So let's talk a little bit more about the nature of dark matter in the universe, because there's a lot of it. Most of the normal type matter is actually dark matter, and it's elucidated not necessarily by this head-tail radio galaxy, but that's usually intercluster gas, which doesn't necessarily push back against it, but that's the evidence of the hot intercluster gas from, say, an active galactic nucleus that's jetting stuff out the sides. So there's a large amount of dark matter that we saw previously, where dark matter makes up much more than like 90% of all the normal matter in the cosmos is dark matter, and we still do not know what that stuff is. Okay, so the next thing we can do is we can say, well, if we probe the universe on large scales, we can actually map this intercluster gas, because quasars are incredibly luminous. Quasars, remember, are active galactic nuclei that can be up to 10 or 100 trillion times the luminosity of the sun, all coming from something incredibly small, only a few tens of astronomical units in size. And this particular one, which is 3C273, is about 5 billion light years away. And it's incredibly bright. We see this jet of material coming off the side from the active galactic nucleus. However, we can map the intercluster medium, or the medium of gas between us and it, by looking at the spectrum. So if we take the spectrum of, say, 3C273, which has a redshift of 0.158, we see it has a bright emission line at Lyman-alpha, which is hydrogen emission. That's due to the hot gas that's falling into that supermassive black hole in the center. And we also see some absorption features along the way. However, if we look at a much higher redshift object, something at a redshift of 3.62, this quasar 1422 plus 2309, which is kind of designated by its location in the sky, we see roughly the same shape to the spectrum, except it's got all these absorption lines at specific wavelengths. And so we call this the Lyman-alpha absorption line forest, or the Lyman-alpha forest. And this is a result of intervening gas clouds between the quasar and us at different redshifts. So it absorbs the ultraviolet light at that specific wavelength of Lyman-alpha, which is the transition in hydrogen between the ground state and the first excited state. That's where that comes from. And so this is a spectrum from M. Rausch et al. They're looking at high resolution quasars in their study. In any event, this Lyman-alpha forest is characteristic of the quasar light passing through these clouds intervening. So there's many clouds in between them, and those gas clouds are because of the distribution of hot hydrogen gas that is all throughout the cosmos in these clumps and bumps along the way that absorbs the light. And so we can then say, well, how does that affect the production of the structure? And we look then see and say, well, we've got these enormous structures, and here's from the 2DF Galaxy Redshift Survey. We can see these filamentary and loops and sheet type structures with large voids. And so there must be these enormous gas clouds that permeate all of these filaments, where there's nothing in the void-like structures, but there's sheets and walls and filaments, and that's where the gas clouds are, and that's also probably where most of the dark matter is too. So we can map that dark matter distribution by looking at the path of light as it's being bent by the light coming from distant galaxy clusters as it passes through, say, like some distant far galaxy. As the light passes through a foreground galaxy cluster, the light's path gets changed. Remember, general relativity says that the shape of space-time is made by the curvature of space-time is made by mass. And so light then follows the shortest path, which is a curved light. But to us it would look curved, but to light it's the straightest possible path. And that curvature in space-time is due to the incredible mass of a galaxy cluster, which might be 10 to the 15th solar masses. And as light from distant background galaxies passes through, it is lensed and distorted. And we can see that in this image, of Abell, of galaxy cluster Abell 2218, lensing background galaxies, and we see a phenomenon of strong gravitational lensing. And this is a Hubble Space Telescope imaging. We see lots and lots and lots of gravitational lenses throughout this thing. We see these arcs and bendings of light that come from background galaxies. And so the galaxies act like some crazy, crazy lens, which then distorts the images of the distant background galaxies behind them. And we can see these, there's a like in almost to the left-hand side, we see this reddish sort of arc, and we see a bluish sort of arc, and then we see outer thin arcs. And those arcs are what we mean by the distant background galaxies whose light was going in one direction, but because of the mass of the galaxy cluster has redirected the light so that we see it. Otherwise, we wouldn't see it because it's going through the galaxy. It would be going over there, but the light gets bent in its path such that we see it. And basically, we can think of this as galactic astigmatism, because that's exactly how ophthalmologists study astigmatism in the eye. They say, what's the thing that's causing the crazy redirect of the eye? And so they make glasses to affect that. Much more graphic representation of the same thing was done by NASA as part of that public release. And we can see the foreground galaxy cluster, which is a big, big ball between us and the Earth. And then what we see in the sky is that kind of fuzzy image that's kind of in the background. But the far more distant galaxy is in that wedge behind. And so the light leaves the far more distant galaxy, comes through the galactic cluster, and then bends around. And then we see it as where we think it's coming where the red arrows come from. That's where we see it to come from, because we don't perceive the bending of it. We just see where we see it. And so it got bent and got put into those positions, but it's not actually at that position. In fact, those things are mirror images of the same exact galaxy that are far, far, far in the distance. So we see one galaxy, two images, and that two images are both distorted because they pass through the gravitational field of this massive supercluster of galaxies. So where did this mass come from, and how did this all occur such that we can map it? In fact, doing this kind of de-astigmatism allows us to actually map the total mass of the cluster. That's how we know it's like 10 to the 15th solar masses and such forth, because you have to have that much mass in order to make those shapes. Next, we can see that there might be, say, not just like galaxies, but maybe even far more distant quasars. So sometimes people say, well, there's a foreground galaxy in the middle, which is those two spots. But then we see that there's two bright spots on either edge, and those are quasars. And they vary at exactly the same time. Every quasars have variability on the order of a few days or weeks, and they can vary in X-rays on the order of hours. And so if these two objects change and they look like they're very far apart in the sky, the two blobs in the upper left and lower right, they are being gravitationally lensed by the two big galaxies in the center, which is probably a galaxy cluster. And those are just the two brightest objects in the galaxy cluster that we see in invisible light. So the galaxies themselves in the foreground are in the middle, and the quasar is in the background. And in fact, the quasar gets to look a little bit brighter because more light gets to us from these locations because of the lensing, so it concentrates the light. And how we can explain that is by sometimes we find four images like around some sort of galaxy. So we got these blue dots. Those four blue dots are the distant background quasar, and the red splotch is the foreground galaxy. So we get the much more distant background quasar that then has its light going around the distant galaxy in the foreground, and as it does so, it redirects the light. And that can be seen here in this particular galaxy area called HEO 4352031, which is a fantastic example of a cross-like gravitational lensing. Those four spots are a single distant quasar, and the galaxy is almost directly in front of it, and it's distorting it and lensing it so that we see four spots around it. And notice this galaxy is itself in the middle of a group of galaxies, but the quasar that is the four spots is far, far, far more distant than all the rest. And this is, of course, a Hubble Space Telescope image that was taken a while back. All right, so where does this mass come from? Where does the gas come from? Where does the structure come from? And how do we know that there's dark matter and all that kind of jazz? All right, so the formation of large-scale structure is interesting because cosmologists and astronomers have known that galaxies can't have formed just from instabilities in normal matter starting from the early cosmos. And this is known because it takes too long for galaxies to fall together. So if it was just plain old normal matter, what we see with our eye, if you then say we have 13.8 billion years to create these structures, they do not go fast enough. They can't create the structures we see fast enough. Simulations have been run, computer simulations saying take a whole bunch of dots, see how long it takes for them to fall together, and it takes more than 13 billion years for them to do it. So it can't be the case that there's only normal matter. And so the background radiation before decoupling, meaning at the cosmic microwave background, before that decoupling, radiation kept it in balance. So you have to start the gravitational collapse after the last scattering surface. So from the last scattering surface of the cosmic microwave background to today is all the time you get. And that's certain, and there's a certain smoothness to the cosmic microwave background and a certain lumpiness to the local distribution. And transforming from smooth which is smooth to 1 part in 100,000, as we saw with respect to the cosmic microwave background, to today, which is incredibly lumpy with lots and lots and lots of galaxy clusters and quasars and things like, well, quasars are distant, but very dense galaxy clusters nearby. That's not smooth, and that's not seen in the cosmic microwave background. It's only seen locally. So they must have happened. The problem is that the overall expansion of the universe would have wiped away. So it could only have had 50 or 100 times, the density of its surroundings, just normal stuff. So that's not enough to actually do the job. However, the dark matter doesn't care, because remember, dark matter doesn't interact with light in any way. So dark matter could have started forming lumps well before the last scattering surface of the cosmic microwave background, because normal matter like protons and helium nuclei and electrons would certainly feel the light and be thermalized by it. But dark matter doesn't do light, so therefore it can collapse, so it can start clumping a long time before. So here's where we got some kind of good cartoon to kind of show it. The vast majority of the cosmos is dark matter. So in the early epochs of the universe, started from, the universe is 3 minutes old, till when it's 300,000 years old. That's what we're going to talk about here. So in the early universe, maybe when it's 3 minutes old, the normal matter and the dark matter were all kind of smoothly distributed. And then, because dark matter doesn't interact with light, and once the temperature dropped enough, the dark matter could start forming clumps around it. And those clumps would form waves and lumps inside of the dark matter. But the normal matter is not bumpy yet because it's still bound to the light. Once it becomes, so the dark matter can make extraordinarily deep peaks and deep gravitational wells into which the normal matter can then fall. So as time goes on, after a few thousand years, and then after about 1 million years or 100,000 years, then you can get these galaxy clusters and lumps that happen much later. So you can create the perturbations in the dark matter and let it run, and then by the time that you get to the cosmic microwave background time, the last scattering surface, then the lumps and bumps in the cosmos can then fall into the hills of the dark matter and form galaxies. So let's kind of see what that looks like in a real good check. So if the universe is 1 second old or a couple minutes old, it's all smooth, mostly dark matter with a little bit of normal matter. And the normal matter then the dark matter starts compressing at about 1,000 years or so. Now, remember, the normal matter has to wait for 300,000 years before it can start playing the game of fall together under gravity, and it does so after about 300,000 years, and then by the time we get to 100 million years, galaxy clusters have formed, and then billions of years later we get lots of stuff going on. So at about 10 to the 8th years, which is 100 million years, we start seeing strong dark matter clumps, and normal galaxies and clusters start to form about 1 billion years later. So that happens at extraordinarily high redshift, a redshift of about 10 or so. Remember, the redshift of the cosmic microwave background is about is about 1,000 or so. And so when we look at the nature of when things begin with galaxies, that's redshift 10 or 20 or 100 or so. So that's when those things are happening. Now, structure can be then modeled using computer simulations. And these simulations were performed at this particular one was performed at the National Center of Supercomputing Applications by Andrey Kravtsov at the University of Chicago, and one of my thesis advisors, Anatoly Klypin at New Mexico State. So there's a big shout out to one of my thesis advisors who was on my defense committee at New Mexico, Anatoly Klypin, creating a wonderful little simulation that shows us from well before the epoch of reionization at Z roughly about 30, which corresponds to very far back in time, less than 100 million years after the Big Bang, is where this particular simulation begins. And what they're showing is that we're showing filaments, clusters and filaments of cold, dark matter, and with some dark energy in there. Now, the frames show, each frame shows about structures that can go across to about 140 million light years, and so the box goes from redshift 30 to about redshift today, meaning now. And what this means is that we start the universe when it was 1% of its current age. That's pretty long ago, 1% or less than 100 million years old. And the distribution of matter seems to be uniform. And then the seeds fall in really rapidly. The matter falls in together rapidly at that time. Now they grow incredibly large to form filaments and structures. And so the entire box from left to right becomes more and more prominent with time. So these filaments form extraordinarily rapidly. All right, so at some point the contraction seems to be halted because as we get closer and closer and closer to our time, we deal with we're looking at the co-moving space of the universe as it expands along with. So this box actually is co-moving with the expansion of the universe. So you actually have to kind of think that this box is also expanding at the same time as the material is falling together. So that's a very complex simulation. I'll place that web link online for you to see. Right, but more recent simulations, such as the Millennium Simulation Project, look at very, very, very large distributions of matter, and it starts in a cubic region with the size of a box. That's 2 billion light years on a side, and this is called the Millennium Run. There were over 10 billion particles in it, and it was used and the supercomputer at Max Planck Society's Supercomputing Center in Garchberg, Germany. It took about a month to run the simulations I'm about to show you, and they applied some really sophisticated viewing techniques to model this of 25 terabytes of stored output. So they've run this enormous simulations, figuring, well, there's some dark matter, there's dark energy, we input this way of gravity behaving, these particles are in this way. And then what they find is that they say we're looking for exactly how things distribute each way. So we see inside of here the redshift start at about 18, not as far back as the previous, but this starts at about 200 million years after the Big Bang, and it goes to the present day epoch. So we're looking at something that might be approximately 500, see they use 500 megaparsecs is how big that little line is, but they divide it by h, which is some fraction of 100 compared to the Hubble constant. So 500 megaparsecs divided by h means the size of this thing is about 700 megaparsecs. So that's what that line indicates, about 700 megaparsecs. Anyway, as we let this thing progress through time, we see by redshift of 5, some structures are forming at the sizes of about 500 or 500 megaparsecs. They're beginning. And by redshift of 1, which is when we start seeing quasar activity, actually quasar activity starts earlier, right about redshift 10 or so. But what we see is that by the time it's redshift 1, where most of the quasars have turned off, we have very strong filamentary structure inside of the box. So then by today, we have extraordinarily tight structures, and this maps the dark matter distribution. That's what this is showing. This thing is showing the dark matter distribution throughout the cosmos. So now let's zoom in and zoom in by a factor of 4 and look at it again. We're going to look at that central region again and zoom in by about 4 times bigger and 4 times closer. So again, we see a smooth distribution of matter with some seeds in it, as the galaxies are roughly smoothly distributed at a redshift of 18. And by a redshift of 6, most of the quasars again have turned off, and so we start to see the beginning of the formulation of dark matter lumps into which galaxies can fall. By the time we get to redshift of 1, the dark matter filaments have been very fully created, and there's something bright going on in the center, and by redshift 0, we've got something really tight going on. So let's take a quick look into just that central region as we go for, again, something only about the size scale of the Laniakea Supercluster. So this is about the size scale of the Laniakea Supercluster, which is really interesting. So by the time we get to today, we've created something that's about the same size as a supercluster. That's really interesting. So other simulations, such as the Eagle simulation, and this was done by Rob Crain and Jim Geach over at Durham University in the UK. And what we're looking at here is the intensity of cosmic gas and dust. And the color indicates the temperature, and red says it's about 100,000 Kelvin. And that's considered warm. And then the white is about 10 to 100 million Kelvin. So this is the evolution of the hot gas inside of the cosmos as it's going. As time evolves, we can see the redshift and the age of the universe in the lower left. And what happens is that as the universe evolves, supernovae are exploding in galaxies, and they heat the gas such that now you have all this intra-cluster super hot gas. And so this simulation is showing us where the super hot intra-cluster gas comes from that we saw in all the Chandra X-ray images. And this comes from the massive formation of galaxies and starburst galaxies, and as the stars blow up, they form this gas that then doesn't cool off. There's no easy way for it to cool off. And this particular simulation is approximately 25 megaparsecs across, and it's a co-moving volume, meaning we're following along with the expansion of the cosmos. So we're actually stretching the box as the universe expands with this particular thing. So it's a 25 megaparsec co-moving volume is what they call it. Now, this particular simulation was run again by Rob Crain at Leiden University and Jim Geach at Hertz University at the UK. All right, but they have other versions of it, and they just say, please credit us. So here's another one of their fantastic simulations, and we're showing now the distribution of cold dark matter. We're going to show a large number of how things move. So cold dark matter is the stuff that doesn't do light. So at the early epochs, there's a whole bunch of cold dark matter that's falling together, and now we zoom in and look at how gas is cooling. So now we're looking specifically at hot gas. It's cooling around some rotating disk at the center of some big dark matter halo. So the dark matter halo is making gas fall into the center that makes a hot rotating disk. And we can see some outflows, some puffy gas as stars explode. And now we end this thing by looking at starlight, and we've basically modeled a Milky Way. And that's what they've done, is by fusing together a bunch of models for stars and gas and dust, they've created a model that actually can create something that's very similar to what we see in the Milky Way and the local cosmos. And that's the idea with these simulations, that's to show how galaxies form, how they grow, how the black holes at the centers of them can grow, and that's their big idea. So their goal was to show something that starts about 7 billion years after the Big Bang, and we can see that we formed a disk-like structure, and that's one of the more interesting things about the Eagle simulation. So I'll pop those and you can go check them out on their website, which shows how the dark matter distribution now ends. So galaxies are at the centers of dark matter distributions that once was smooth and then fell together, and that's what that's showing. Next, they have another really fascinating thing where we're looking at an amazing thing. So looking at this large-scale distribution of gas that's colored by temperature. Blue is about 10,000 Kelvin, and red is about 1,000,000 Kelvin. So this is actually showing how the gas evolves, and you can also see stars and galaxies inside of this. So it's kind of a mixed thing of all these things. And at the object that we're going to get to at the end, there's a massive, supermassive galaxy cluster that's being formed in the center of this thing. And that's about the mass of the Laniakea Supercluster. Again, we're creating supercluster-size objects that are in the centers of these things. We can see how gas is being funneled along into the shapes that are being channeled by the dark energy content. So now we can see where the Lyman-alpha forest comes from, because here's all the dark the hot gas that's in between the galaxies, and now we've got a Laniakea Supercluster inside. And as time progresses, we then can model the idea of nearby, we can model the idea of how gas forms. Now this also explains why nearby quasars like 3C273 don't have a big Lyman-alpha forest, but things at redshift to say 3 or 4 do. Because things that are redshift 3 or 4 have to pass through many of these clouds, but something at smaller redshift only passes through a void because the clouds have been cleared out by this time. Notice in the deep, deep, deep past, before all this structure forms, the clouds are very evenly distributed. And now once you get to the later portion of the simulation, the clouds are confined to these filamentary structures. And deep in the center is something the mass of the Laniakea Supercluster. And that's what these simulations try to show. Next, we actually kind of look at their simulation again, and this shows 3 different views of the simulation that we just were flying around in. The left-hand 2 images on top and bottom show the dark matter distribution. The middle, pardon me, the top one shows, the top row shows that if the stars that explode as supernovae don't interact and don't push as much gas out into the cosmos, then the gas can stay put and form galaxies. The bottom row shows that the supernovae that occur in these early galaxies has a big effect, and the gas gets spread out really massively very quickly. And on the far right-hand side is the visible light due to galaxies. So now we see more massive gas. So the visible light is on the right, far 2 right-hand sides of stars in galaxies. And we can see that we see more galaxies in the top row than the bottom. The bottom row, though, shows that dark matter doesn't really get affected by these supernova explosions, but the visible light component does, and the X-ray component would. So these different simulation runs actually can be used as test models and compare them against observations of, say, X-ray emission by galaxy clusters, as well as the distribution of the Lyman-alpha forest in distant quasars. And also you can say, well, how many galaxies do we expect to get out of the lower simulation compared to the upper simulation? And if you get fewer galaxies than observed, such as the bottom row, then that might not be the correct way things are going. But if you get something more similar to today, which might be the top row, then at the end, on the upper right, you say, yeah, the simulation must be in the right track because we're making Milky Ways, and that's what we see. Finally, this is another look at how dark matter evolves with time, and this is again the Eagle simulation. Once again, this is about 100 megaparsecs on the side, this particular box, and at the end, this whole box is large enough to contain the mass for 10,000 galaxies, like the size of the Milky Way or bigger. So this is basically simulating the formation of a supercluster of galaxies such as Laniakea. So that's what we're getting. So this is an enormous computer simulation that took a month and a half of computing time on the Dirac 2 supercomputer. In fact, it took 4,000 computer cores on a supercomputer to do it for a month and a half with 7 billion particles falling together. So this isn't just some movie that was made up at Skywalker Ranch or something like that. No, this was made by a massive supercomputing facility over in Durham, UK. And that's what the Eagle simulation is, and so you can give those guys over there a big howdy-do, because those are some amazing websites, and I'll post them on my YouTube channel. Finally, we can then take a look at the comparison between what those simulations do and take slices through those simulation results and compare them to what we actually see. And so when this Millennium run, which was something I looked at very early on, was run, it was one of the largest simulations. And it used about 1 billion particles to follow dark matter. And the goal was to see exactly how things formed as things starting from about the size of the small Magellanic Cloud up to extraordinarily large objects like giant elliptical galaxies. And what we find is that these particular galaxy clusters, and there's the real one, there's the data taken by the CF2A, the Center for Astrophysics, that's the Great Wall, there you see it, and the Sloan Digital Sky Survey shows wall-like structures. And those wall-like structures, these can actually be simulated. And so let's go take a look at what they kind of look like. So the Millennium simulation creates those wall-like structures. So you then do statistical analysis on the actual appearance of the simulation versus the appearance of what you see in the sky, and you try to get them to be exactly the same. It's amazing that the Millennium simulation basically creates what we see in the sky. And finally, we can go look at, say, something like the 2D FGRS survey, which is in the different directions of the sky, and we can see the foamy structure that is there, and then compare that to the Millennium simulation. We see the similar foamy structure that exists there. And this is part of the Millennium run, and it's used looking at a particular kind of cosmology, meaning most of the universe is dark matter, where it's about 75% dark matter and about 25%, we call it 70% dark matter, 75% dark, in that range, and about 25 to 26 or 20% dark matter, 70% dark energy, and about 25% matter and dark matter. So that's called the Lambda-CDM benchmark model, and that's what creates these simulations, is that if you have matter, dark matter, and dark energy in the right proportions and let things go and make the simulations, you create what we see in the sky. So where did we get the idea to use 70% and so forth? Because this computing time, you don't want to spin that up. That comes from looking at the formation of large-scale structure can be deemed and dictated by the statistics on the cosmic microwave background. So the ripples and lumps and bumps that are on the order of 1 part in 100,000 on this thing, the temperature differences between the hot red and the cool blue, are 1 part in 100,000. So they're really tiny temperature differences, and that means they're very tiny mass differences. And that means there's tiny, tiny, tiny asymmetries, which then get reflected later. So this is called the last scattering surface, where light was interacting directly with matter, and from this time, when the universe was about 300,000 years old, at this moment, the universe then expands away, and the atoms, the hydrogen, the protons and electrons combine to form hydrogen atoms, and the electrons combine with helium atoms, helium nuclei to form helium atoms, and all of a sudden the light can stream freely from the cosmic microwave background to us. But as it does so, it passes through a huge amount of material from the cosmic microwave background formation at the last scattering surface until it reaches us. And so as structure forms, we see in this simulation of how structure forms, we take the, say, the Millennium simulation, and we plow it across, and there we see larger and larger structures forming as time progresses. And this is also the dark matter map, so dark matter simulation, since dark matter is most of the matter in the cosmos, and dark energy is very smooth, so it doesn't actually form lumps. Dark energy doesn't form lumps, dark matter does. And so once we've created a map of the dark matter path through it, the light then traverses through that dark matter path and gets bent in its directions from then to now. And there are slight asymmetries that can be measured on the cosmic microwave background as it does that. So here is the path that the cosmic microwave background photons take as they traverse the cosmos to us and pass through all of the structure that's being formed. In the early parts, after they first become free, the through which they pass has almost no structure. But as they travel more and more and more, before they reach us, they get redirected more and more frequently because of the structure that has formed. So the path gets more and more wiggled, which distorts the appearance of the cosmic microwave background. And since it distorts the cosmic microwave background, you can actually measure that effect. And how you measure that effect is by looking at hot and cold spots on the surface of the cosmic microwave background and analyzing the statistics of how hot and how cold it is at given angular size scales between two patches of the sky with the same size, but different temperatures for different orientations. And as we saw in the previous thing, as the light, these lumps and bumps get changed from the original last scattering surface appearance by the intervening dark matter and normal matter, because sometimes the normal matter interacts just by by scattering it through an electron, scatters it off that hot gas. But that actually can be measured statistically. And this is the power spectrum, or the amount of the degree of bumps and lumps or waviness in the cosmic microwave background. And the two arrows that I'm pointing out show that the ratio of these two peaks, and every pair of peaks like that, every pair of peaks, not the first peak, but the second and third, and the fourth and fifth, the ratio of those two peaks, how high they are, and what the amount of what the power is, which is the temperature fluctuation in microkelvin squared, what that amount is, gives you the amount of dark matter in the universe. Because dark matter, as we saw, doesn't slosh as much as normal matter does. So it actually forms these, it just kind of falls together and doesn't bounce around. It just simply falls together. So it increases, so there's this difference that as it falls together, it doesn't recoil as it falls. It simply falls together slowly. Now, the second peak shows how far, but then you got blobs of material, of dark matter, or normal matter actually, so that there's blobs of normal matter, and they kind of rattle around inside of the peaks that we saw earlier on, that are created by the dark matter. So those things rattle around inside there. So sometimes they get close and sometimes they get far. And so the second peak, which is not the tallest peak, but the second peak, shows how far apart the biggest blobs of normal matter got, and that's the angular size scale of about 8/10 of a degree. And the third peak shows how compressed the biggest blobs of matter got, and that is about 3/10 of a degree. So there's a lot on the sky. So we see how that these two measurements show the springiness and movement of big blobs of matter that would eventually become superclusters were moving around in response to the dark matter distribution that we saw making those peaks in that earlier slide. So we can then think of this as like saying, well, okay, the springiness of it is that the normal matter is like a guitar string, and a guitar string vibrates, right, in air, and that's why we hear it being plucked. But if you pluck a guitar string underwater, it dampens rapidly, and so the amount of dampening, it vibrates slower. And the ratio of these two peaks it demonstrates how much dark matter there is, meaning if one peak is much taller than the other, then they dim out rather rapidly, or they're very close together in terms of their size scales. And we see, well, the power on one size scale is much less than the other. And then we could use those two measurements to actually give us the total amount of dark matter compared to normal matter. That's what those two peaks show us, and the ratio of the heights of the two peaks. And as a result of that data that was gathered by looking at the cosmic microwave background, the important things were discovered by looking at that, and one of them was that the Hubble constant, or today's value of the Hubble parameter, is 67 kilometers per second per megaparsec, with an error of about 1 kilometer per second. But the more important thing is that we find that the energy density compared to the critical density for dark energy is about 68.5% of the universe. Roughly 70% of the universe is dark energy. Now, the baryon density and the cold matter dark energy density is basically the rest of it, because by that time, by today, the cosmic microwave background forms practically nothing of the energy density, even though it's lots of photons. Remember, it's gotten redshifted down to microwaves, so it doesn't contribute much. So we've got dark energy, normal matter, which is baryons and the baryonic density, and then cold dark matter, which is density. And if you compare the numbers between how many grams per cubic centimeter the dark matter is compared to the normal baryonic matter, we see it's about 5 to 1. So cold dark matter outnumbers the normal matter by 5 to 1, or there's like 80% dark matter and about 80-90% dark matter energy density compared to about 10 to 20% normal matter. So the other two parameters that can be derived from just that curve alone, with the green fit curve to all the dots, which are the data points. The dots are the data points taken by the Planck probe, and that's where this particular curve comes from. And the green line is the best fit values that give these numbers. So from this, we learn how much dark energy density there is in the universe, as well as the age of the universe is 13.8 billion years. Finally, we can extend that a little bit and find something really fascinating about it to tell us what the total amount of energy in the cosmos is that we know the total amount of normal matter is known to about 1% precision, and dark matter is known to about 1.4% precision, and dark energy is not as well known, to about 3.7 or about 4% precision, but that's really good. And that together, combined with the other data, shows that the total energy density today of the universe is 0.099995 plus or minus 0.034. So that means it's basically flat. So 0.9995 plus or minus 0.034 or minus 34 is consistent with a flat universe. And that's what we gather from that. So we say, oh, it must be a flat universe composed of dark matter, mostly dark matter, dark energy, dark energy mostly, and then dark matter makes up the rest of the cosmos with a small sliver of normal matter in there. And plugging this stuff back into those simulations and then having the normal matter show and do normal things, we saw that the simulations can create Milky Ways, they can create the structures that we see, they can create the clouds of interstellar gas that we see, that create the Lyman-alpha forests, they can create the dark matter distributions that make the galaxy lensing that we saw. So this is an incredible triumph of basically confirming the Big Bang as a concept. So we say that why is it part of the Big Bang? Because if the universe had a birthday, then it had a baby picture, and it had an adolescent picture, and a childhood picture, and it had an adult picture. And so things change with time. If the universe did not have a beginning, then we should be able to look 13 billion light years away, or maybe 20 billion or 100 billion light years away, and see something exactly like the Milky Way. And that concept was called the steady state theory. But the Big Bang says that, well, if you look farther back in time, you don't see that stuff. You only see smooth distributions. You see galaxies in these primordial forms, and that's what we saw in the Deep Galaxy Survey video that I did, is that early galaxies are tiny and misshapen. But now we can actually utilize simulations to actually demonstrate the structure of the galaxies combined with the cosmic microwave background to confirm that we actually have all this back stuff that actually can show, combining the cosmic microwave background with computer simulations, and what we can learn by that, we can compare that to what we see for distributions, simply where galaxies are in space and time. And that tells us basically that the Big Bang actually did happen. And if it didn't happen, something an awful lot like it did. So if it didn't happen, something really close to it did. And this is one of the more important features, and that's why people love running these simulations, because they look pretty cool. All right, so we'll see you next time as we look at very soon at these odd elements of the cosmos, such as cosmic inflation and what's going to happen to the end of the universe. See you soon.